So a question I get somewhat frequently in DSC 10 is people have taken a stats class in high school, or maybe they've heard about things like p-values. And their question is, how does the p-value I learned in this class relate to the p-value I learned in high school? And the answer is they're the same thing. Okay? In high school, you probably learned about the normal distribution if you heard about p-values. And the normal distribution, you have a way of calculating p-values if you assume that your data is distributed normally. And in this class, the cool thing is we never assumed that anything is distributed normally. We never use the word normal distribution. And in fact, we will in the next couple of lectures. But we haven't assumed anything about the distribution yet. We plotted it. We used simulation to figure out what that distribution is, what the histogram is. And so by now, hopefully, you kind of have an idea that, hey, this distribution thing, that's important. I need to understand something about the distribution if I'm trying to do a hypothesis test or construct a confidence interval. And so what we're going to do now in this last part of today's lecture is learn about simple descriptions of the shape of a distribution. Where is it centered and how wide is it? So those are simple questions. How do we identify where a distribution is centered and how wide or how variable it is? And then we still need to answer this question. If you've kind of noticed, a lot of the distributions that we've plotted so far, they look kind of bell-shaped. And the question is, why is that the case? And then one lingering question after that is, I have an idea that if I get a larger sample, that increases the accuracy of my estimate. But how exactly are those related? And so those are questions that we're going to be able to answer here in the next couple of lectures. So the first thing that we might do in order to measure the center of a distribution is we compute the mean. So for instance, if I have data 2, 3, 3, 9, the mean is calculated by adding all of them up, dividing by how many numbers I have. So the mean here is 4.25. A lot of times people call this the average, but that's not technically speaking correct. This is a type of average, the mean. So let's talk about a couple of properties of the mean. So first of all, the answer doesn't need to be a value in the collection. So as we saw here, I had 2, 3, 3, and 9. The average, or the mean, was 4.25. That isn't one of the numbers I had. It doesn't need to be an integer, even if all of the data are integers. And this is sometimes a problem. For instance, if you want to ask, like, hey, what's the number of, what's a typical size of a family, right? Well, if you calculate it, you'll see that, most families have, the average family or the mean family has 2.5 children. Of course, they don't have half a child. It's just that the mean doesn't have to be an integer. So that can be a little bit confusing, or maybe not what you want in your particular application. Maybe you want typical to be actually a typical family. And we'll see in a second, the median will give you an integer if all of your inputs are integers. So the mean is somewhere between the minimum and the max, but it's not necessarily right halfway in between. It's not the midpoint. Okay. For instance, if I have 1, 2, and 10, the mean is not 5. It's 13 divided by 3, whatever that is. So the mean has the same units as the data. So if I compute the mean of a bunch of temperatures, the unit that I get of the result is temperature. And you can consider it sort of a smoothing operator. This is kind of a more mathematical look at things. You're collecting all of the numbers into one big pot, and then you're summing up all of their contributions, but then you're distributing them evenly. So if you have like a tax-paying system where like you have a bunch of people, some of them are very rich, they're all contributing, they're making contributions to one big pot, but then you're taking all the contributions and you're distributing them evenly. It's a very equitable system. So the median, on the other hand, is just a number in the middle of the data. So to compute the median, I sort the data and then I pick the number in the middle. Now, of course, sometimes there can be two middle numbers if I have an even number of numbers. Okay. So for instance, if I have these 5 numbers, I sorted them, the median will be 7 because that's the number in the middle. If I have an even number of numbers, here I have 4 numbers, a median of this data set is any number which is 4 or 7 or between 4 and 7. Okay, so in this case, 4 is a median of this data set, 7 is a median, but so is 5. So is 5.13. Okay, it doesn't have to be a number in the middle. But oftentimes what we do is we adopt a convention which just says, okay, a median here is, I could call it the lower median is 4, the higher median is 7, whatever you want to do. Or sometimes you'll see people say that the median, excuse me, the median of an even number of numbers is I take these two and then I take the mean of them. They're just different conventions. So oftentimes it makes sense to pick a median so that it's in the data set. You can choose whichever you like, 4 or 7. But it doesn't, it depends on exactly what you're going to use the median for, which median you want to choose. Okay, so for instance, suppose I have a distribution. Okay, so these are, I don't know, these are scores on a homework. Okay, and here's my distribution. So the most popular, the most frequent score was around 3. Okay, can I compute the median of this distribution, and can I compute the mean? Okay, without actually knowing what the scores are or writing them out. Okay, so you can write them out. You can kind of create a data set which has this histogram. In this case, you could see here I have twice as many 2s as I have 1s, twice as many 3s as, or sorry, looks like 3 times as many 3s as I have 1s. And so you can see that it looks basically like 1, 2 2s, 3 3s, 2 4s, 1 5. And in fact, any multiple of this, so I could double the number in each group and the distribution would look the same. But what are the median and what are the mean? So I'll give you a second to think about this. Oh, look, I reproduced the histogram, so my guess is right of what the data set is. Now, with this data set, with this list of numbers, you can compute the median quite easily. Okay, so it's going to be 3, because that's in the middle. And if I look here, that's the median. It's the mid, it's sort of the 50, half of the values lie to the left of this, half of the values lie to the right. So the median is here. The mean, I'll calculate, you can calculate either by taking this and actually computing the mean. So we could use numpy.mean here. Okay, it's 3. Or you can kind of also recognize that in this case, the mean, right, is sort of one of the ways that you can think of the mean. It's like if these were all weights that you were placing on a teeter-totter, the mean is where you would put the fulcrum so that it balances. Okay, that's like a physics explanation of the mean. And you'd see I'm going to put it right in the center so that it balances. And again, the center here is 3. So here's a question I'll let you think about for a second. I've got 2 distributions. Call this distribution A, or distribution X. This is distribution Y. Are the medians the same or different? Are the means same or different? And if they're different, say which one is larger. So I'll let you pause the video and think about it for just a second. So there are kind of 2 ways of answering this question. First, you could try to figure out what the actual values are, what the distribution, what that array is that gave rise to these distributions, and I'll let you do that. But the second way of doing it is to kind of reason out the answer, and I think it's the preferred way because you understand more about the difference between the mean and the median. In any case, okay, so let's take a look at the median first. Okay, so does the median change from here to here, from X to Y? And the answer is no. The median will not change. Why is that? So I'm taking just the last value here, this, I guess 5, right? And I'm just increasing 5 to 10. Now, if I think about that array, what's going to happen is I'm just making the last entry larger, but I'm not changing the middle entry, right? So since I'm not changing the middle entry, the median's going to stay the same. Let's look at the mean now. So the mean, I'm going to add up all of these numbers, and I'm going to divide by however many numbers I have. Now the number of numbers isn't changing, so the denominator isn't changing between these two. But what is changing is the numerator, the sum. It's getting larger here. So the mean is going to change. The medians are the same, the means are different. It's answer B. So we can check that out by trying to figure out what the new distribution is, what that new array is. Remember, I'm just taking the last entry here, 5, I'm changing it to 10. So I have table 1 and table 2. I'll calculate the medians and the means of both. You see that the medians are the same, the means are different, and the mean increased because I'm increasing the numerator but keeping the denominator the same. All right, so comparing the mean and the median. So the mean, like I said before, the kind of physics way of viewing the mean is it's the balance point of the histogram. The median is the halfway point of the histogram. Half of the area of the histogram is to the left of the median, half is to the right. If the distribution is symmetric about a value, then the mean and the median are the same. So we saw here, for instance, the mean and the median are the same. But if the distribution is skewed in one direction, so for instance, it's kind of skewed to the right here, then the mean and the median are different. Okay, the mean is pulled away from the median in the direction of the tail. You can think of it kind of like this. Actually, there's a discussion question coming up, so I'll let it go for that discussion question. But first, in this data set here, which is larger, the mean or the median? Okay, so again, we have a tail here. It's not a symmetric distribution, so they're not going to be the same. We have a long tail going to the right of flight delays. The mean is going to be pulled in the direction of the tail, so the mean is going to be larger than the median. Let's check it. Yeah, so the median is 16 minutes while the median is 2. One of the nice properties about the median is that it's more robust to outliers. So a lot of times we have a choice. Do we use the mean or do we use the median? And what I want to say is that oftentimes the median is the better thing to use. So let's look at an example. Suppose I went out and I gathered the net worth of all UCSD students. So I have their mean net worth. Suppose it's $529. At least that would have been a lot whenever I was in college. I didn't have $500. But the median net worth is $238. Okay, so the mean and the median are somewhat different, and that's because the mean is pulled up by people with a high net worth. So if I were to take a look at the histogram, see I have a long tail here. This is totally simulated data, by the way. The mean is going to be pulled to the right because there are people with a higher net worth. Now suppose Jeff Bezos decides to enroll as a data science major, and I think this is old data, so let's see. Jeff Bezos' net worth, $188 billion. Okay, so let's change this to 188 billion. So Jeff Bezos is now enrolled, okay? The net worth of UCSD students, well, the mean is going to change quite a bit. The median, let's see. So let's see what the new average or the new mean net worth of UCSD students is. So it's $9,400,059. That's just due to one person, okay? If I compute the median, it's $238. Okay, it didn't really change. Didn't change at all. Or no, it did. It did change a little bit, okay? The median is not as sensitive to outliers. Jeff Bezos, in this case, is an outlier. If I ask the question, what's the typical, net worth of a UCSD student? You don't have Jeff Bezos in mind, right? So the median is probably the more appropriate number here. Okay, so the standard deviation. So you've probably heard of the standard deviation before. We're going to use it to measure the width of a distribution. So one of the first things we might think of, so let's throw out everything we know about the standard deviation. Let's just try to derive or come up with a measure of the shape of the distribution, how wide it is. So the first thing we might do, it's called plan A here, is take the biggest value minus the smallest value. This tells us something about the width, but it has some major drawbacks. So first of all, it's sensitive to the largest value and the smallest value. So remember, if Jeff Bezos enrolls at UCSD, all of a sudden this number just gets huge, the difference between the biggest value and the smallest value. What I want to know is what's the typical sort of width of the distribution of the histogram. And this doesn't really tell me that. It doesn't tell me much about the shape. On the other hand, we have this number called the standard deviation. And it turns out that this is a better way, in some sense, of measuring the width of the distribution. What the term standard deviation literally means is like, what's the typical difference between a number in the data set and the mean? So it's a good measure of width. So let's see it in action. So I've got an array here. Here's my data. Remember, the mean of this is 4.25. Okay. Now I want to measure something about how wide this distribution is. In a typical case, how far are we away from the mean? So I'm going to take the deviations. This is the difference between a data point and the mean. So remember, my data here is this, and my mean was this. So I take each of these numbers and I say, how far is it to the mean? 2 minus 4.25, it's 2.25 units to the left of the mean. 3 minus 4.25, it's 1.25 to the left of the mean. That's why it's negative, it's to the left. And then 9 is 4.75 units to the right. That's why it's positive. So these are all of the deviations. I don't want to just find the average deviation, right? So this is kind of a measure of how far I am from the mean, right? This is, the larger this is in magnitude, the further I am away from the mean. So what's the sort of average deviation? Well, I could take the mean of the deviations and I get exactly 0. And this is not a coincidence. You can check with math that it's always going to be 0. The mean of these deviations is going to be 0 because I add them all up. I'm going to get 0 in the numerator. So what do? Well, I don't really care whether I'm to the left or to the right. I'm going to take the absolute value of this. I'm going to take the absolute value of the negatives, and that'll give me the deviation, or that absolute deviation. But it turns out that we don't actually do this that often. It's totally valid to do this. It turns out what we do instead is we square it. And that'll get rid of the negative sign as well, but it gives us a different number called the variance. So I'm going to find the average squared deviation. Okay, so let's take a look. I'll take my deviations, I'll square them. That gets rid of the negative sign. And now when I take the mean, I get 7.68. Okay, so the larger the average squared deviation is, the variance, the larger the variance, the more spread out the data is. Now, you might know the standard deviation is the square root of the variance. So that's the definition of the standard deviation. So I'm going to take the variance and then I'll take the square root. Why do we do this? So suppose our data has units with it. So for example, minutes. And I want to figure out, what's the standard deviation? What's the width of my distribution of data that contains minutes in it? If I were to look at the variance has weird units. It has the units of minutes squared, and I don't even know what that means. What is a square minute, right? So the correction is you just take the square root. It's as simple as that, and I'll take the square root of the variance. I'll get the standard deviation. Okay. So the standard deviation is the square root of the variance. We have a NumPy function for it, numpy.std. It takes the standard deviation. So I have my data. We computed it before, it was 2.77. And we see here, yep, that's right. So the key here is that the standard deviation contains or measures roughly how far the data are from the average, and it has the same units as the data. That's why we might prefer the standard deviation to the variance. But they both give us similar pieces of information. So the key here is, why do we use the standard deviation? Remember, I said, well, one thing we could do here is we could take each of the deviations and we could take the absolute value and then take the average of that. And that's something called the mean absolute deviation from the mean. That's a totally valid thing to do, but instead of doing that, we don't take the absolute value, we take the square. Okay, we square each of these, sum them up, or we square each of these, compute the mean of the squares, then take the square root. It's not the same thing. Okay, so why do we do this and not do the mean absolute deviation thing? Well, the answer is that the math for the standard deviation tends to work out nicer. It tends to be that the standard deviation is a bit more meaningful in terms of the mathematics that you're going to be doing. So here's why. Basically, no matter what the shape of that histogram is, I can say something like the bulk of the data lies within a few standard deviations of the mean. And to make that more precise, we have an inequality, a famous inequality in statistics called Chebyshev's inequality. So whenever I say the bulk of the distribution lies within a certain range of the mean, here's what I mean more specifically. So no matter what the distribution is, it could be bell-shaped, it could be like have a bunch of hills, it could be have a long tail like with the airline data. No matter what the shape is, the proportion of the values that are within z standard deviations of the average, so from average minus the z standard deviations to average plus z standard deviations, is at least 1 minus 1 over z squared. Okay? So I make an interval. I say, okay, let's start with the mean. Let's go out 2 standard deviations. So I get my upper bound, I get my lower bound, 2 standard deviations away, and I'm guaranteed that 1 minus 1 over 2 squared, so 3/4 of the data, lies within that interval. So this is kind of a cool inequality because it doesn't matter what the histogram is. So let's take a look. Like I said, Chebyshev's inequality tells me that within 2 standard deviations of the mean, I must have at least 75% of the data. I could have more. Okay, this is a sort of lower bound. It's a lower guess. It says you have to have at least 75% of the data, and that's a guarantee. You must. It's not like you'll probably have 75% of the data. It is you will have at least 75% of the data within 2 standard deviations. If I crank that number up, 2 go up to 3 standard deviations, I'm making my interval wider. I'm going 3 standard deviations up, 3 standard deviations below. I must have at least 1 minus 1 over 3 squared, which is 88% of the data. If I go all the way up to 5 standard deviations, I'm guaranteed to have at least 96% of the data. And so this is why we use the standard deviation specifically, is that there's this theorem for it. It's a very simple theorem, Chebyshev's inequality. I mean, this is one reason we use the standard deviation. There are others, and there are some reasons that you would want to use the mean absolute deviation as well. But here's a nice thing about the standard deviation. So let's take a look at an example. I have NBA players, and I have their heights. So if I look at this, I've got the mean height of an NBA player is 79 inches tall. So I can look at the distribution here. The mean is about right here. Notice that this distribution is not really bell curved. Okay, it's kind of a skewed bell curve. It's kind of like ramping up here and then it drops off because there are really not that many players above 85 inches tall. Not that many humans above 85 inches tall. So I can use Chebyshev's inequality to tell me something about how many players lie within a certain band around the mean. The standard deviation here is 3.45 inches. The mean is 79 inches. So at least 75% of the data is within this interval. So I take 79 minus 2 standard deviations, 79 plus 2 standard deviations. That gives me the interval 72 to 85. Chebyshev says at least 75% of the players have a height in this interval. And then it says at least 88% of the players have heights within this interval, which I compute by replacing 2 with 3 here. Now, you'll notice that Chebyshev's inequality works no matter the distribution. That's kind of the cool thing. But if we know the type of the distribution or the shape of the distribution exactly, if we know more information, we can say more. We can get better bounds. We can get better information. And so what we're going to look at in the next lecture, in the next couple of lectures, is, hey, what if we know that our distribution, what if we know that our histogram is a bell shape, that it is a normal distribution? If we know that, we can say a lot more things. And in fact, we won't have to run the bootstrap and do all this stuff. So we'll talk about that. But just to give you a hint, it says at least 88% of the data is in this interval. If I go back here, 89 inches, nobody's more than 89 inches tall. If I knew exactly the shape of this histogram, I could calculate exactly what percentage of people are in this interval. But if I don't know it, I can just rely on Chebyshev's to give me sort of a coarse kind of guess.